We can just start there. Going forward, easier. The agenda was really brief. Basically, just said we're going to do our little intros. I'm going to be covering a section on CLC Light's incentive offerings. Todd's going to be actually doing the big lift here. You'll be doing the majority of the training here on the refrigeration optimization. We will have a Q&A section at the end. So any like big questions or really specific questions you might have, maybe save them towards that area. But if you do have any kind of small questions or anything that kind of, oh yeah. And if you do have any small questions that kind of make sense to answer within the flow of our conversation, please do interrupt. Raise your hand in the room or online, Katie. If people throw something in the chat, let us know. We will also be trying to take a break right around 9:30, about halfway into the presentation. Might not be exactly there. We'll try to do it at a nice break point, but somewhere around halfway through the presentation, we will be taking a pause. I am Theo Frey with CLC Light. I'm an energy management analyst. I help implement our commercial and industrial energy conservation programs. These are a few different types of measures that we're going to talk about today. In the past, right up until the end of this last year, each one of these different types of measures had a different incentive rate. So we used to offer 27 cents for capital improvements, 24 cents for new controls, and just 10 cents for durable operations and maintenance, or durable O&M. But we've actually gone ahead and overhauled our rates, and now we're just giving a flat 33 cents for all of these different types of projects. I think capital improvements and new controls are fairly self-explanatory, but by durable operations and maintenance, basically what we mean is any kind of project where you're not actually replacing any of the existing equipment or controls, you're just operating the equipment you already have in a more efficient manner. So lowering set points, those kind of things, and then documenting it for us. Those tend to have a pretty low cost because there's not a lot of capital involved, and really it's just kind of the labor. So those can be kind of a home run win-win project for you guys. Yeah, can you advance me, please? There we go. I know the text on the screen is way too small, but really I just wanted to give you guys an idea that we offer incentives for a whole bunch of different types of projects. Today we're specifically talking about refrigeration, but really any type of energy conservation measure that you guys are considering, there's a good chance we can help pay for that choice. Okay, so anything you can think of, lighting, HVAC, multifamily weatherization, data centers, the whole breadth of those projects we can help you guys with. So do reach out for any of those kinds of projects. Next slide. But wait, there's more. So not only do we offer those, what I'm going to call our base incentives at 33 cents per kilowatt hour for most of the projects we'll be talking about today, but we have these two different supplemental incentives that we're offering now that can be stacked on top of that 33 cents. And each of these is worth an additional 2.5 cents per kilowatt hour. So if you happen to be doing a project that qualifies for all three of these things, you'd have an effective rate of more like 38 cents per kilowatt hour. Pretty good incentive rate. The project development incentive, or PDI, that one is pretty easy to participate in. Really, we just add it to any project that's eligible. Currently, it's time bound. It's only guaranteed for projects that complete by June 15th of this year. I know that's kind of a short time span, particularly for industrial customers. I've heard rumblings that there's a good chance we're going to extend it beyond that date, but I can't verify that right now. So do stay tuned for that information. The other one on here is the Energy Program Manager, or EPM. This one is a little bit more involved. The goal of this one is to really find a specific person that works at your facility or through your operations that can be what we call an energy program manager. And then we'll work with that person to find a portfolio of projects, really just meaning at least more than one. And at least one of those projects to begin with needs to be a non-lighting project, so it can't just be a series of lighting projects. And we need a minimum estimated savings across that portfolio of projects of 200,000 kilowatt hours. And that's really just the starting point. These are a 2-year contract. Our hope is that by enrolling you in this program that you guys are going to have a champion on site that can go through, find more opportunities, and really build out that pipeline of projects for us. There is a cap of $150,000 just from this 2.5 cent measure, so that doesn't affect the other incentives that you'd be eligible for. But to hit that at 2.5 cents, you'd have to find like 6 million kilowatt hours worth of projects. So pretty good problem to have if you do actually hit that. Next slide, please. All right, cost caps. So speaking of cost caps, we do have a few different rules depending on exactly what type of measure you're doing about how much of it on total we can pay. So it's all kind of related to the total project cost. So it gets a little bit complicated, but the general idea is that the base incentive that I've been talking about, that 33 cents per kilowatt hour, that can only cover up to 70% of the total project cost. So if you had a project that cost $100,000 and it was an absolute home run, The most we could pay out in an incentive would be $70,000. That's just for the base incentive though. The nice thing about these supplemental incentives is we're allowed to stack those on top of that 70%. So in theory, we could cover 100% of a project cost. Can't go past 100% because we can't pay you to do a project, but in theory, we could pay for the whole thing. The most likely candidate to run into that cost gap is going to be those durable O&Ms because there isn't a lot of cost up front and you're really just kind of recording your labor costs and whatever small things you need to do. But what we can do is bundle those durable O&M measures with another capital project. So if you happen to have another capital project going on site, we can stick those under one project in our tracking system, kind of share those costs across them and really maximize the amount of incentive that we can get you. Good example of this recently, there was a site that Todd went out to. He found a great change to a refrigeration system where they ended up saving like 300,000 kilowatt hours just from reducing a set point from a durable O&M measure. They happen to also be doing a fast acting door project at the same site, so they're able to bundle those things together, and we were able to kind of maximize the amount of incentive that we could pay those guys, which is really great. Next slide, please. So how do you get this money? How do you participate? The main thing I really want to harp on here is contact us early and often. We want to be your partners out there, not just on specific projects you guys already have, but we'd love to just be a part of the conversation with anything you guys are thinking about in the long-term future as well. So once you have identified an opportunity, we'll review that opportunity with you. We'll probably do some type of site visit. At the very least, we'll do something to collect what we'll call our baseline data. It's basically going to be equipment that's existing there, get some nameplates and models, horsepowers, and how you're operating that piece of equipment as well, how many hours a year it's operating, at what set points, those kind of things. We'll then compare that baseline to whatever the proposed equipment or proposed set points are going to be. We'll estimate total amount of energy savings over the course of a calendar year for 1 year. And then once we've got all that information squared away, put together what we call our participation agreement. That's our basic contract where we put in detail what we expect you guys to be doing for this project, how much savings we think we're going to see from that project, and how much we're going to pay you if you do the project as we expected. Again, I really want to harp on contacting us early and often. It's very important to get that participation agreement signed and executed before you start the project. It's a big bummer, but it's happened more than once where customers have reached out to us after they've already completed some great projects. And unfortunately, we weren't able to incentivize them because we weren't able to determine what the baseline was before they started the project. So do contact us, especially before you do anything to the existing equipment. But once you do have that contract in place, that's when you have our blessing to go ahead, do the actual project itself. We do offer flexibility, so if things need to change, you got to swap out equipment, those things like that, that's fine. We'll take care of that on the back end. If it happens to affect the savings, we would change the incentive as needed. But then we would go through our measurement and verification process. That should be included in the documentation for participation agreement, like what steps we're going to take for the M&V and what we're going to need from you. So hopefully there aren't any surprises on the back end. But once that M&V process is completed, we verified the savings, that's when we can actually pay out the incentive. That incentive can go back to the customer, or if they would like, we can assign it to a third party like a contractor. It's entirely up to the customer. Next slide, please. Energy Smart Industrial Program, just one more thing I want to talk about today. So that's the program that brought Todd to us here. So as far as I'm concerned, it's a great program. It's funded by the Bonneville Power Administration. So Todd doesn't just serve us, he serves several other utilities in the area, and really any utility within Bonneville Power Administration's service territory has access to this Energy Smart Industrial Program. It's a kind of a general program that's there to encourage industrial customers to find energy conservation projects. Not only does Todd do great trainings like you guys are about to see in just a few minutes here, but he's also an active participant in our projects. He comes out to site visits with us, he helps us identify opportunities, he helps us with the measurement and verification process. It's great. Anytime Todd's involved on a project, now it's going to be a pretty easy one for me because he does a lot of the heavy lifting. It's fantastic. The other thing that ESI does are energy studies. I haven't seen us do a ton of these in the time that I've been with utilities, so I'd love to see us do more. Really, the concept here is that if you guys are thinking about any kind of large scale change with your operations that might have some energy savings opportunities involved with it, ESI can have a specialist come out, look at your systems, your operations, kind of estimate how much savings they think you would see from completing that project. And that way you kind of do a bit of a financial feasibility study for that project to know whether or not it's actually worth moving forward with for you guys. One more, I think that was my last slide though. Yeah, this is thank you. So again, please do contact me with any questions you guys might have about our programs. And I'm going to hand the microphone off to Todd now for the main event.
Thanks, Theo. Good morning, beautiful people. I am Todd Toburen. I am the ESIP, or the Energy Smart Industrial Partner, here in the Puget Sound area. And kind of like what Theo was saying, I'm part of BPA. I assist the utilities throughout the Puget Sound region. We serve, I might get this wrong, but I'm pretty sure it's 8 states, 120 some odd utilities. So I know this is all geared towards contractors. So if you are doing a project over in Pasco or somewhere in Idaho or Oregon, you can reach out to me or go to the BPA website, and I will put you in, or somebody will put you in contact with your ESIP. So because this is a contractor-based presentation, we're not going to dive into a lot of, a lot of theory in refrigeration, how refrigeration works. But what we want to do is we want to focus in on where are the opportunities, and what opportunities are incentivizable or energy project, opportunities. Facts and figures sheet. Katie, are you putting this in the chat? Perfect. So we just call this the cheat sheet. It's a great little laminated sheet to be able to take on site with you if you're thinking, and it's just got a plethora list of energy efficiency opportunities, front and back, shows you why it's saving energy, so on and so forth. And then there's going to be another one on there, the best practices guide. And that's what the best practices guys look like. Great reading material in the evening when you're getting ready to go to bed. It's very, very heavily focused on, obviously, energy efficiency in refrigeration systems. So when we're talking about these refrigeration systems, a lot of this is going to be focused on like a built-up ammonia system. But refrigeration is refrigeration. All we're doing is moving BTUs. So whether we're talking about a chiller, an ammonia system, a Cascade CO2, just a package condensing unit sitting on the roof, whatever it is, they all have pretty much the same components that are located. So looking at our 4 major processes, I always follow liquid flow. So coming off of that condenser, we've got liquid going through our expansion valve into our evaporator. That's where our expansion takes place, changes state from a liquid to a vapor. And then our compressor's pulling a suction on that, compresses that gas to a high pressure, sends it back to the condenser. Like I said, whether this kind of depicts a built-up ammonia system, but whether it's your air conditioner sitting outside of your house or a 100,000-pound ammonia system in a big distribution center, it's just the same process. All you're doing is moving BTUs. So what we're going to start off with is compressors, and we're going to focus in on what are some of the different opportunities that we could go on with compressors. Should be a little button to hit start right on the bottom of that thing. It says play. You got it. So here's our compressor running. If you take a look at it, coming up on the top, you can see you've got your screw, your suction's coming in. The red valve, that's your slide valve controlling your capacity. Behind that, the blue thing behind that is your slide stop, which is controlling your volume indexing, or your VI. Discharge into your oil separator, flows back to the left, goes through your coalescers, and then discharges out the top, going to your condenser. And below is all your oil cooling. So there's quite a few different things here that would be opportunities for refrigeration. discharge pressure reduction and suction pressure optimization. I always count these two together because what we call that difference between your suction and your discharge is your lift. And the smaller that you can keep that lift, the more energy efficient that compressor will run. Running that discharge pressure, rule of thumb, and this is on that cheat sheet, for every degree that you lower your discharge temperature, you're going to save 1.5%. On suction pressure, for every degree that you raise your suction temperature, you're going to save 2%. We also have part load control. On that last little video you saw, all we had was slide valve, oil cooling, and coalescent filters. So before I was talking about, lift, you reduce that lift, you're gonna gain higher performance. You raise that suction, you have more capacity, more tonnage. Lower that discharge, you're using less brake horsepower. If you're running at 150 PSI and all of a sudden you lower it down to 120 PSI, that's 30 PSI less that compressor has to push against. So compressor performance is horsepower divided by tonnage. And rules of thumb, again, I already mentioned it, but I'm going to mention it again because it's very important. And I've been doing this now for better part of 25 years, and I've tried to break these percentages, and I cannot. So once again, 2% compressor savings per degree of increase in suction temperature, and then 1.5% compressor savings per degree of decrease in condensing temperature. The difference between the two is because for us to lower that temperature on our discharge pressure, well, we have to run more fans on those condensers. So we are going to use a little bit more power up on the condenser, and that's why it's 1.5%. So let's talk about a little bit of part load. Two absolute rules. Efficiency is worse as the compressor unloads. If you have I don't care if it's a screw compressor, a recip compressor, whatever it is, if it's running at 100% fully loaded, that is when it's most efficient. Second rule, speed control is the most efficient, the most efficient way to part load for screw compressors. This is a great graph. It kind of explains a little bit on why using speed control is so great for part loading. If you look at that red line, that is just our slide valve. And on the bottom, we're looking at capacity, and over on the left, we're looking at percentage of power. And when that slide valve is pretty much like on the screen, if you read it and it says I'm at 0%, you usually still have 15 to 20% capacity of that compressor, but you're still using right around 50% of the power of that machine. If we take a look at a reciprocating in the little green triangle, it's fairly linear. Recips are great part load compressors, especially when they have loader unloaders. But if we look at the VFD, that is almost linear. So at 50% capacity, we're at 50% speed instead of the slide valve. And now we're also at 50% power. A couple interesting things on this graph is you can see once it hits 50% speed, and then it kind of shoots off to the side, it kind of starts following the slide valve. The reason that is because at 50% speed, that's the minimum speed on that compressor. Now there are upgrades with these compressors out there where if you put on external cooling on the motor, then you can run this down to 20% as the minimum speed. But if there is no external cooling, then that motor isn't going to get enough airflow over the top of it to keep it cool. The other really interesting thing is if you look at 100% for the VFD, it actually goes to actually hit the 100% capacity. It goes up above that 100% power. And that's because of those losses across the VFD. right around 3% is what those losses are. So if you have a VFD machine and you're running it at 60 hertz, it's actually costing you more than it is if you just run it across the line. The VFD is doing you no good. You're paying more money for it. We got the same two screw compressors. One has a VFD. What's the power at 60% capacity? Your slide valve is going to be using about 76%. VFD is going to be using about 62%. 14% difference. Doesn't seem like a lot, but you walk into a facility that's got 8 or 10 of these things sitting there, and they're all 800 horsepower. That's quite a bit of energy, especially when you extrapolate that over 8,760 hours in a year. So very, very good saver. But on that same note, if we turn around, same two models, and we run them at 100% fully loaded, the one with just the slide valve is going to be more efficient. That's when it's going to be its most efficient. So what you want to do is you want to base load with that machine that has no VFD, and then you want to trim with that VFD machine. So oil cooling and filters. We'll go ahead and hit the play on that one again. You guys saw this slide a little bit earlier, but what I want you to look at now is down in the oil separator area. There's a couple different opportunities here. One are these coalescing filters, and what those do is they capture that oil and drop it back into the oil separator. There has been strides with coalescers. There's a couple different manufacturers out there that make these things called super coalescers, because what could happen is if you lower your head pressure, sometimes you'll get that velocity that goes a little bit faster in there, and you'll have oil carryover. So that could be a barrier to lowering that head pressure. But these super coalescers, they help out quite a bit. In this case, if we look at the oil cooling, which is at the bottom of the oil separator, right here, they're using what looks to be like maybe a glycol or a water. So there's a few different ways to do it. You've got mechanical TXVs, electronic TXVs, you've got an oil cooler, you have a thermal siphon. Where the biggest savers that we see on that is when you have a mechanical TXV, it requires a pressure differential, and you've got to run your head pressure artificially high for it to work properly. Electronic TXVs work great, and this is a great measure to do on like package systems, little Freon systems that are maybe sitting on the roof, because most of them all have mechanical TXVs. And by putting on those electronic TXVs, now you're able to lower that discharge pressure. All right, moving on to condensers. In my view, one of the greatest pieces of equipment on the face of the earth, because there's nothing to it. You have fans, water pumps, and a big coil. So we're going to talk about evaporative condensers first. They drive towards that wet bulb temperature outside. They're not looking at dry bulb. It's taking into consideration that humidity. It's going to help lower that lift. Remember, we want to get that suction and discharge pressure as close together as possible. Now, we do have to have that differential, so our refrigeration will move, but we want to try to get that head pressure low. Condenser fan VFDs. It's a no-brainer. It's a perfect marriage with wet bulb control and condenser fan VFDs. On package systems, we're looking at VFDs if you've got larger motors, but most commonly what we're seeing now are ECMs, electronically commutated motors. And then condenser water pumps are usually not a great energy project, but it's worth looking at with remote sumps. And what I mean by that is you'll have your condenser sitting up on the roof. and then your condenser water trough or tank will actually be down in the engine room. And always look at the sump heater settings. I can't tell you how many times I've gone somewhere and it's 80 degrees out and they're burning 10 kW heaters in their integral sumps. So I kind of talked about a little bit about the remote sumps for condensers, and this is a great example of what would be a good VFD project on a condenser water pump. You can see that all the valves are discharge valves are throttled. Well, you're still using a lot of energy on these pumps. Why not throw a VFD on it, open them wide open, and just slow those down? So that's the kind of things that you want to look for. I've seen it before where, in fact, I was with one of the folks here in the room where we walked into a plant and it was going out to a chiller and they had 75 horsepower pumps on it. And they had 3 of them running. And I asked them, why do you have 3 running? They said, well, we fired this plant up 10 years ago and all 3 were running. Okay, great. Let's turn one off. And they were like, whoa, we can't just, they all had VFDs on them. I said, no problem. Let's just slow it down to 50%. I think we waited like 5 minutes. So you have this one run 75 horsepower, switch to the next one, switch to the next one. Is that not typically done? Great question. And the question is do they stage water pumps? And it all depends on what facility you go to. And a lot of times it all depends on how that person was trained. Can't tell you how many times I've gone out to places and said, well, why are you doing this? Well, because that old guy over there told me to. And that is a very common answer that I hear. But ultimately, I mean, before we left that site, we shut down a 75 horsepower motor. You know, and that goes back to kind of what Theo was saying, the operation, I mean, the durable O&M projects. You know, you're shutting that 75 horsepower motor off. That's instant savings for 8,760 hours a year. It's a great saver. Nozzles, so water distribution, this is another great one. In the upper left-hand corner is the older designs, 180 degrees. So the positioning of those nozzles was very important. Not only that, but they clogged really easy. Moving up to the newer clog-free nozzles, they distribute water a lot better. This could definitely be an energy project. Obviously, these nozzles, they're plastic, but they're not cheap. But if you're able to lower that head pressure, now you're saving energy. That's an energy project. And condenser capacity versus scale. I love this slide. Keeping those condensers clean. Now, this could be a big ammonia condenser with scale on it, or it could even be, you know, bird feathers that are caught up underneath the air cooling condenser up on the roof. But if you take a look at it, and I want to say a penny is a 1/16 of an inch. So that reduces your capacity to about 55%. Scale is a great insulator. And what happens is you don't get that heat transfer, and now you're not rejecting that heat to atmosphere. It's just sitting there in the ammonia, and you now have to run that, you got to run that head pressure artificially high. Purgers, non-condensable, I'm sorry, go ahead, Theo.
Just real quick on that last slide. So while that is really just kind of a maintenance thing, cleaning the condenser, if you're able to then lower your set points, that would be a durable O&M measure for us. It pay you for something like that.
Yeah, and if everybody heard, that was, if you can lower your head pressure by doing that, it's definitely a durable O&M. Auto purger, another incentivizable project. If you have a lot of non-condensables, let's say you're doing some blast freezing, you've got some spirals or some IQFs that you've got to run your system in a vacuum. Very possibly you're going to pull in some air. Whenever you break that system open, if you don't pull that down to 30 inches and leave it overnight, you're going to pull in some air. Putting in an auto purger and removing that air in the system is going to lower that head pressure. Because if you've got those non-condensables, you may be running 120 PSI, but if you've got 10 pounds of non-condensables, you could be running at ammonia saturated pressure of 110 PSI. So that 10 PSI is going to be quite a bit. Moving on to evaporators. Capacity control for evaporators. So there's a few different ways you can do this. Fan cycling, and what that means is when the space hits temperature, if your space has a temperature set point of 35 degrees, space is at 35 degrees, the fans just shut, your liquid valve shuts off, your fans shut off. Constant fan operation, and they just cycle the liquid solenoid valve. If they are doing that, fan cycling, or the last one, variable speed drives, VFDs, are going to be your big savers. We're doing one here in Seattle right now with a large produce plant, and it's going to be a great project. But VFDs absolutely work great on these evaporators. On package systems, usually they're ECMs. And there is a misconception out there, even on these built-up systems. If you've got an evaporator with 5 fans on it, you don't have to buy 5 VFDs. If you've got 5 1-horse fans, you buy a 5 horsepower VFD, and it operates all 5 fans. So it can be less than what you actually think it is. And this is the beautiful thing about VFDs. We get to follow the affinity or the cubic laws. And so at 50% speed, it's not 50% power. And the reason being is it is a variable torque load versus a constant torque load would be like a compressor. And the way I always looked at it is if I have to turn the shaft by hand and it won't turn on its own, that's a constant torque machine. But like with a fan, if I could spin it and it continues to spin, that's a variable torque machine. Because once it gets up to speed, it doesn't need that same amount of torque as it did at startup. So now we're going to get to use this curve. Well, at 50% speed, we're only using about 12.5% of that power. And even when let's say you do walk into a plant and they already have VFDs. Another great opportunity is to cap that speed. If they've got VFDs, they're probably running them at 60 hertz when it's starting to get a little warm in there. But if you turn around and you just cap the speed on the VFD to 90%, well, you're only using 78% of that energy. So now you'll never go into that 3% of the losses on the VFD. Defrost is always a big deal on evaporators. Defrost types: hot gas defrost, electric defrost, air defrost, and there are still freezers out here in the Pacific Northwest that use water defrost. Obviously, air defrost is the most efficient. Fans just run a little bit more for a little bit of time. Hot gas is right up there with air defrost. Most expensive, most of the time, is electric defrost. Now, hot gas could be more expensive than electric, and I'm going to talk about that a little bit later. But why I put up there the systematic defrost optimization, it's because one doesn't need a defrost. Most of the time, they don't. Get that nice frosty coil. That way, when it melts, it cleans that coil, get rid of the condensation that comes from the coil, and now you're done. But let it run out, let it build up frost. Most of the time, most of the evaporators I see, they're not even ready for defrost. Had a site over in Eastern Washington that could never make temp. They had over 100 evaporators in the facility. Every evap was defrosting every 4 hours. Well, all they're doing is just dumping heat into the space. So that's what we're going to do. The reality of defrost. The percentage of heat that actually used to melt frost. So 15% is used to melt frost. And then we've got warm melted frost or condensate that is going down the drain and hopefully out of the freezer or wherever it's at so it doesn't freeze. And we've got about 20% that's used to heat up that coil and all the metal on it. But then 63% is lost to the room. That's just more heat that's getting put into the space that your refrigeration system has to remove. So now if you turn around and you extend that defrost out because you think there's something wrong on your evaporator, you go, okay, we're gonna run an hour of hot gas or electric defrost on this. Well, guess what? The frost is gonna be gone. So you can't melt any more frost, so it's all gonna be lost to the room. So really optimizing that defrost and making sure you're not putting an excessive amount of heat into the space that you later have to remove is very important. And this is a great example of a durable O&M project. You know, if you are, and the reason why I say that is if you optimize those defrosts and now those fans get to cycle more and turn off more, or they run at that lower speed, now you're saving energy. Across a defrost management plan systematically, start with clean coils. I cannot stress this enough. Start with clean coils. I've had folks say we clean our coils every 6 months and I go roll cardboard off of it like it's a carpet. Okay, that didn't happen. You got to start with clean coils and address problem evaporators. If there's an issue with, you know, the temperature difference on that coil or it's not performing the way it should, go up, start looking at the valve groups. Look at that, look at your liquid valve, look at your strainers, look at your expansion valves, look at all those things. Address the source of infiltration, keep frost out. I know we're sitting here talking about refrigeration and more refrigeration and moving BTUs, but high-speed doors, they are great. Theo had just mentioned about, you know, when he was up here, he was talking about the brewery we did a project at. I walked by, they wanted a high-speed door. They had a garage door that they just kept open all day long, metal garage door. And we went and looked at their chiller, walked by, they were running 448 as their refrigerant, and they were running 290 PSI on their head pressure. Got a big smile on my face while we were there. We threw some loggers on it, got a baseline, came back 2 weeks later, talked to their contractor, lowered that head pressure, shooting for about a 70, 75 degree condensing temperature. When it was all said and done, about 350,000 kilowatt hours a year, which is great because now what did we do? We just combined it with the door project and the door was paid for because the actual cost of the project to lower that head pressure was me on the phone with the contractor said, hey, is it okay if we do this? And he said, yeah. And because the contractor just said, yeah, he didn't charge him for that time, which was great. But that's a great example of a durable O&M project. And it's things like that where we can help you guys as the contractors sell that project. You know, especially with doing a study or saying, hey, this is an incentive that could be attached to that. And one thing you can't forget about is that 350,000 kilowatt hours that they save a year. That's about $35,000 a year that comes off of their energy bill. So that also needs to be taken into consideration. Make changes gradually. Check the evaporator pans daily for signs of frost buildup. Keep an eye on it. Yeah.
So ideally you want to be at 15% out frost or best efficiency.
Mm-hmm. Yeah, absolutely. When I was in industry running a large ammonia system, it was a pain, but I'd go up there, get a nice frosty coil, starts my pump out. Then I go into my defrost and I stand there with my phone. I hit the timer. And once I see that the pan is clear of condensate, my defrost is done. I did that for summer. I also did it for winter because you're going to get a lot more humidity and you're going to, a lot more heat. We want to do a quick break. Yeah. Come back. Come back at 9:40. How's that? 9:40 it is. Making command decisions. Everybody got their coffee? Got a donut? Something? There we go. So where does our frost come from? Dock doors, freezer doors, product, walls, ceiling penetrations, water defrost. If you do have to do that, people or other. You know what? Freezer doors or cooler doors, they're a big one. A lot of times when I see these installed, it's kind of the industry standard. They install the door and it has a 10-second delay. Industry standard is actually 3 to 5 seconds. Don't ask me why they just didn't say 4. I have no idea. Whenever I do a door project, we put it at 4. It makes a big difference. Especially if you've got an evaporator that sits right up above that door. Wall, ceiling penetrations, this is something that if you've got if you have issues with your envelope, that is an energy project, definitely an energy project. And just people running around there. We're small little energy plants. We put off heat. But keep the frost out, that's number one. Control systems. So there's a bunch of different control systems out there. It's getting a lot better than it was 20 years ago. You have your central control systems for like a built up refrigeration plant, like an ammonia or a CO2 plant, something like that. Then you also have your individual unit controls. And that would be like a key to therm or something similar to that. They both work great. And they both do the job. You're going to get the fan cycling. You're going to get all the bells and whistles you need to be more energy efficient. So what can we look at for controls on compressors? Sequencing, floating set points, proper VIs. These are great little things that you can do where it's just O&M. And you'll be able to save a lot of energy. On the condensers, floating head pressure, group fan control. So if you've got VFDs on those condensers, having those fans work together, it's a great opportunity. Defrost bumps. Earlier I was talking about hot gas was cheaper than electric defrost. But with a defrost bump, let's say that you've got an evaporator that is a quarter mile away from the system, and you know what? You have to run that head pressure at 130 pounds at least year round, just to supply that with a defrost. But if you had a defrost bump, you could run at 100 to 110 pounds all year, and the only time that your head pressure would go up to that 130 is when that evaporator goes into defrost. So that's a great little tool. Evaporators, group fan control. Group fan control is where all the evaporators are working together. They're all running at the same speed. They're all cooling to the same temperature. It's great for an individual space where the temperatures are the same and they all ramp up and ramp down together. Fan cycling, floating temperature set points, which what happens is if you hit set point and it's off hours and nobody's going to be in that space, well, there's no infiltration taking place. So let's take that and you know what, we had it at 34, we can go as high as 38. You know what? We just don't want to reach 40. So we'll let that float all the way up to 38. Runtime defrost, another great one. Be able to turn around and just base your defrost off of cooling time. Instead of having to kind of guess or schedule your defrost with a date and time, just base it off of how many hours has this thing been cooling? Because if you're able to turn around and say, all right, my fans are cycling, my temps are good for the last 4 hours. Well, if you schedule every 4 hours, it's going to go into defrost no matter what. But if you do runtime defrost, now it's going off of actual cooling hours. And then I alluded to this a little bit earlier, cap that maximum speed on those VFDs. If you've got a VFD on the motor and you're able to keep it off of that 100% speed of 60 Hertz, what I always see works really, really well is 90% capping it at 54 Hertz. What you lose in CFM is negligible. And if you don't believe me, that's great. You're not the first person not to believe me. Test it. Turn around and cap it at 59 Hertz and see if there's any changes. If that's good, take it down to 58 Hertz. You know, so do all of these gradually, especially if you're not quite sure. Controls. This happens to be a centralized ammonia control system, and this was a great project. You can kind of see, you know, the different types of controls that you have. This was with Seattle City Light. It was a big project at a big freezer plant, and we had done the measurement and verification, but they weren't running any of the set points at what they said they would run them at. So what we did was me and Seattle City Light went in there and we sat down with them for a morning and we held training. And the nice thing about this project was they had all the bells and whistles on their control system. And so when I would say, okay, you know what, if we do this, this, and this, you know what, your temperature is going to come down in that space and then your fans are going to slow down. And we made the changes. 5 minutes later, temperature starts dropping, fan starts slowing down. I think another one was compressor sequencing. All right, we're gonna change your suction pressure from this to this, and you're going to maintain your temperatures, but you're gonna hear that compressor slow down. And as soon as we made that change, about 2 or 3 minutes later, you could actually hear the compressor slowing down. Next slide. This is just another screenshot from that same control system. Like I said, there's a lot of different opportunities and a lot of different areas that you can look at. This is just the layout showing all the spaces with the particular evaporators in each space. This, another one right here, we spent quite a bit of time on this. This is the defrost screen. And folks were, we went through, I think they had about half of them that they weren't using runtime defrost. They had that opportunity. So we put runtime, we put them into runtime defrost, and now they're better able to manage when the defrosts were going to take place, keep that heat out of the space. So a little tool belt if you're going out into the field and you're kind of going, okay, this is a lot to digest. But tool belt for compressors. Look at that suction pressure. First and foremost, what's the space temp requirements? It's a pretty easy calculation to kind of just say, okay, you're running ammonia, you're running 404A, you're running whatever refrigerant. What is the temperature requirements for your space? Get that nailed down first. And then what's the coil TD? What's the operating temperature of that coil? Most of them for a freezer, 8 to 10 degrees. If you're in a cooler, you're upwards of, let's just call it 13 to 15 on the high end. Look at the discharge pressure. Can they use wet bulb control? Can they control that head pressure to wet bulb? Or if they don't have an evaporative condenser, we're looking at dry bulb on a package system. What is the minimum condensing pressure? Pacific Northwest, it's beautiful up here. It's nice and cool. We're not down in Florida, so we don't have to deal with all that humidity and everything else. 100 PSI is pretty standard. I've worked at some Apple storages, Eastern Washington, Eastern Oregon. 80 PSI year round is what they run. Very, very low. But 75 degrees, it's a great target to go for when you're looking at that. And once again, is there a defrost bump? Because I talked about the advantage of a defrost bump. There's also a disadvantage of that defrost bump. And what that is if they have that defrost bump in there and it's not specifically designated for an individual evaporator, well, every time something goes into defrost, it will bump that head pressure. And if they're over defrosting, which is very likely they are, then something is always in defrost. So they could have the 100 PSI minimum condensing pressure, but because something is always in defrost, they're running 130, 140. Condensers, do the fans have VFDs? If they don't, great project. Those projects, condenser fan VFDs are usually pretty quick ROIs, quick paybacks. What's that max speed set at? Let's cap that at 90%. Look at that water distribution. Do they have good water distribution? What do those nozzles look like? Are they the 180s or are they 360s? Making sure they've got good distribution. Clean coils. Don't want to see any scale buildup, anything of that nature, dirtying up those coils. We want that heat transfer to be seamless. Throttled valves on pumps. Take a look for those. Evaporators, fan cycling, or VFDs. If they just run continuously, I promise you, it is a great project and it's going to have a very, very great ROI. Doing a project for fan cycling right now in Seattle City Light territory, and it's going to be a no-brainer project. They're moving forward with it. Group control, if you've got those VFDs, make those VFDs work together. All those evaporators work in unison. So they're ramping up and slowing down together. Take advantage of those, of the affinity laws, cubic laws. Remember, 50% speed, you're still getting a lot of cooling out of it, but you're only using 12.5% of the power. So take advantage of those VFDs, cap them at 90%. Clean coils, very important. Very important to have those clean coils. That goes right back to defrosting properly. And standardized temps. You know, a lot of times when, you know, the folks at the site, they're paid to, I always say, paid to keep the cooler cold and the freezer frozen. They're not so much paid to save energy. So a lot of times you'll see standard temps, space temps should be 35. Well, they'll turn around and they'll go, okay, well, this one over here is set at 33. This one's 34. We're going to do this one at 35. And they'll stagger the temperatures in that space to kind of just keep airflow and everything going, which if you just turn around and use group control, you'll always have that. You'll always have that flow going through there. And when you get in there, if they've got a control system, screenshots. Take a ton of screenshots. And the reason why I say that is, you know what, you're going to leave that, you get to go to that site for an hour or two. Get the screenshots, because when you get back to the office or you get back somewhere, now you can start going through those, really start going through those screenshots, because that's where you're going to find a lot of opportunities. Now that's whether it's a centralized control system on a built up refrigeration system, or if it's even a, you know, package units that have ketotherms or another type of control system on there. Get as many screenshots as you can. Because when you get back to the office and you're able to actually spend some time to go through them, you're going to find a lot of different opportunities, or you're going to have a lot more questions where, hey, why are you doing this, or why are you doing that? And then you can go back to them and say, hey, you can save energy here, 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 here. That's all my side. I'm going to hand the baton off here.
All right, am I in the camera? Which way do I need to go? Oh my God. Okay, so thank you, Todd, for that presentation. You're a great teacher. We could give him a round of applause in the room. Yeah. And just to reiterate what Theo said earlier, to get started with a refrigeration project at Seattle City Light, give us a call. A real quick number to have in your pocket is the 684-3800. The energy advisors will get you set up with whatever project you're working on. Their email is there too. And actually, I think the next slide has Todd and Theo's personal information to give them personal questions, not personal questions, you know, personalized. And I'll hit that next slide in just a second. And now I think we're just going to do Q&A. So you have to stand back up and come up here, I think. Yeah. I'll go back to the computer and monitor chat. Robert's going to help me monitor chat or questions. If those of you online have questions. Let's see, what else? That's it. I'm going to hand the mic to you. Go back to my computer.
Thank you, Katie. And remember, I mean, we've talked a lot today about Seattle City Light, but you know, this is everything that they do here in Seattle is ESI territory. So if you're doing a project somewhere in the Pacific Northwest and you want to know if there are incentives available, you don't know who to talk to, there's my information there. Just reach out, shoot me an email. There's my phone number, give me a call, and I should be able to point you in the right direction. All right, any questions in here while we're looking at the chat? Alex. Mm-hmm.
Sites where they don't have as built out of the control system. Something would need to be implemented for that.
Great question. So the question is with like runtime defrost, do they already have those capabilities, or is it something where they would have to upgrade their control system to be able to have those capabilities, right? And the question is yes and no. And the reason being is I've seen a lot of places where they do have great controls and they have that option, but it's kind of that old school mentality where I've always done it this way before and I'm going to continue to do it this way. So there's going to be a discussion and talk to. Now that would be a durable O&M if we were able to do that. But if they don't have that capability and they do a controls upgrade, then that would just fall right into a custom project. And that's still going to pay out at 33 cents a kilowatt hour here in City Light territory. Yes.
I don't understand why it saves energy.
Because with fan grouping, what happens is, let's say you've got, good example, you've got 2 evaporators. Each evaporator is 5 horsepower total. If you wanted 50% capacity on that, right, you're going to turn around and you're going to just run 1 evaporator. So you're running it 5 horsepower. If you have VFDs and you run them group control, now you've got all your fans running, but you're running at minimum speed, 50% capacity. Now you're only using about 1.2 horsepower versus that 5 horsepower. And that's kind of a rudimentary example, but you know, you get into some larger plants, and it doesn't even have to be larger plants. I mean, I've seen a lot of plants that just have a lot of evaporators, but getting them to work together based off of capacity and slowing those down with the VFDs. Yes.
So on defrost, is temperature differential like across the coil better than one time?
So the question is temperature differential better to initiate a defrost versus runtime? I'm going to say runtime is better. There's been a lot of different technologies that have tried to change the way you initiate defrost, frost buildup indicators, airflow differential, or temperature differential across the coil. What ends up happening is those sensors break, and a lot of times they don't get replaced. The only thing you're playing with is your temperature sensor and your solenoid valve, liquid solenoid. As soon as that liquid solenoid valve closes, you know, it initiates that defrost, because you know that, you know what, it takes 12 hours in the winter and every 6 hours in the summer. I know I build up enough frost on that coil. So that's what I want, is that time in cooling, and not so much based off of just a time of day. Now, there are a lot of places that have so many evaporators that they do have to stagger them off of time of day. But with the control system, you can also set up a queue, and you can say, I'm running liquid runtime defrost, but I only want 2 coils in defrost at any point in time. So you might have 2 coils in defrost, there's 2 other coils that are ready to defrost, but they just kind of sit there and keep on cooling in the queue, waiting for those to be done. So you're not dumping a lot of heat into the space all at once.
I know you talked about this applying to all the refrigerants, but with some of the newer refrigerants coming online, are there any changes that you expect or are seeing already?
Refrigeration is refrigeration. You're just moving BTUs. I mean, even like a built up CO2 cascade system or a transcritical CO2 system, there's still opportunities out there. And you're still worried, you know, your suction and your discharge, that's always going to be a thing. Just because you run a high discharge, it's hard for that compressor to push up against that. It's all pretty much the same. You're just moving BTUs. We are quite, yep.
How about thermal energy storage? Are you seeing, we really touch on that, but wondering if you're seeing more of that, or you see more potential for that to do load shifting, energy savings in general?
Great question. So it's thermal energy storage, load shifting. I've seen a couple sites around the nation that are trying out the thermal storage. I know there's quite a few different technologies that are out there. I haven't really seen it take over. But for like demand usage and load shifting, you know, freezers, coolers, it's a great place to do it, because usually they always have a great envelope. You know, so if you're able to shut down your refrigeration system, or not even just shut it down, but just take your pressures and raise your suction pressure and raise your space temperatures for a given period of time, it's pretty easy to load shift in some of these larger plants, because they'll just maintain that temperature for a pretty good period of time. Nothing in the chat? Oh, Stern, Robert. All right, we know who the fun police is. Yeah.
So I have kind of a general question.
Mhm.
This is also here. So you, it's a common language to everybody. So you see many grocery stores with coolers, and there's no covers or anything like that. I realize you're going to get into stocking and things like that. All of that cold air is lost. The motors have recycling quite a bit more than you have cases or something like that on it. Just like there's good opportunities.
There, I would believe that. I've never done any like grocery store beer coolers, but I think the exact same thing anytime I go in there. It's horrible. I walk in and I look at it, refrigeration. I'm just like, oh, you got to be kidding me. You're wasting energy.
We'll pay about $320 per linear foot for adding doors to open case, medium temperature display cases at a grocery store. So for a beer cooler, $320 per linear foot for doors.
Somebody online give me a thumbs up saying you heard that.
I can't remember the number, but BPA also recently introduced a unit energy saving measure for.
It's a flat $300, and there's a good chance we're going to be adopting that eventually. So now is a great time to get your contract in, is to get that extra $20 per foot.
Okay, there you go.
All right, if you got any beer coolers, yeah, give City Light a call. You're going to get more money than what BPA is given.
Also, need to say a lot of these things that you're talking about today also apply to grocery stores. So we're focused on large warehouse refrigeration systems, but the same concepts apply to anybody that's got a big refrigeration space, just on a slightly different scale.
Yeah, just to reiterate what Theo just said, it's refrigeration. If you've got a refrigeration project, call it in. We'll determine if it's commercial, if it's industrial. We'll put it in whatever category that we need to put it in, and we're willing to help you guys out.
All right. Thank you, everybody, for coming virtually and in person today. Another hybrid experiment for us with one of our partners. Thank you, Smart Building Center, for letting us have the room, and to BPA for letting us have Todd. Reminder, there's a little survey at the end to take for you virtual people. Uh-oh, we got a weird message on our system here. I guess it is time to go. And I'm gonna go back to my computer, close this out, and hopefully visit lightingdesignlab.com to see our next webinars. They're not usually hybrid like this with AV equipment that we don't know how to operate. But anyway, thank you, and we'll see you next time.